In part two of this lecture, we'll spend a few minutes talking about what's called the standard hydrogen electrode. If you recall, when we introduced this table of standard reduction potentials, we said all of the values listed here are referenced against a defined value of 0 for the reduction of hydrogen ions to hydrogen. We could write this reaction, or any of these reactions, recall, as oxidations instead of reductions. If we do that, we need to change the sign of the E0 value. If we look at the reference reaction, that means we can write it as a reduction, as it is in the table here, and it's assigned a value of 0 volts. But even if we reverse the reaction and write it as an oxidation, it still would be 0 volts, because the last time I checked, when you change the sign of 0, it's still 0. If we want to use this reaction as a reference electrode, or in other words, a reference half cell, we need to physically build an electrode that could possibly run in what we call reductive mode. In other words, hydrogen ions being reduced to hydrogen, or if necessary, to run in oxidative mode, which would be hydrogen ions going to, hydrogen gas being oxidized to hydrogen ions and electrons. In addition, if we want this to be a standard hydrogen electrode, of course, the hydrogen ion concentration would need to be 1 molar, and the partial pressure of hydrogen gas in the cell would have to be 1 atmosphere. Again, we could call this half cell then the standard hydrogen electrode. Let's look at what a possible physical setup would be and how our reference electrode could run in either oxidative mode, where hydrogen gas is oxidized to hydrogen ion, or reductive mode, where hydrogen ions are reduced to hydrogen gas. The physical setup of a standard hydrogen electrode would consist of a piece of platinum metal. Just to make sure you know, the platinum metal here is just this little tiny square. Remember, platinum is very expensive, so if we're going to use it, we'll use very little of it. A piece of platinum metal that's immersed in a 1 molar solution of hydrogen ions, and that has 1 atmosphere partial pressure of hydrogen being bubbled over the electrode. This is a very odd and kind of scary looking setup, but the idea here is right at the platinum to have both hydrogen gas available at 1 atmosphere of pressure and hydrogen ions available at a concentration of 1 molar. If our half cell is running in oxidative mode, what we have here is hydrogen gas being oxidized to hydrogen ions and 2 electrons, hydrogen gas being oxidized to hydrogen ions, electrons leaving the half cell and going to carry out a reduction in an attached half cell. Again, this would be the standard hydrogen electrode running in what I call oxidative mode. Hydrogen gas being oxidized to hydrogen ion, electrons leaving and going to the other half cell while a reduction is carried out. Or we could run it in reductive mode. So here we'd have electrons entering the standard hydrogen electrode from an attached half cell, and the electrons enter here, and at the platinum metal surface we have hydrogen ions being reduced to hydrogen gas. Again, hydrogen gas is present in 1 atmosphere of partial pressure, hydrogen ions present 1 molar concentration. This would be the standard hydrogen electrode running in reductive mode. Now let's see how we could use this electrode to construct the table of standard reduction potentials. And what this will involve is attaching this hydrogen, a standard hydrogen electrode, to other half reactions to see whether those half reactions force the standard hydrogen electrode to run in oxidative or reductive mode. Here's a abbreviated table of standard reduction potentials that we'll use here in a minute. And here's a very complicated looking diagram. Well, what do we have here? Well, we have the standard hydrogen electrode in this diagram on the left. The standard hydrogen electrode is right here. And on the diagram on the right, the standard hydrogen electrode is right here. Let's go back and look at the diagram on the left. What we've done here is connected the standard hydrogen electrode to a copper 2+ copper half cell. Well, what seems to be going on? Well, when we do that, electrons flow from the standard hydrogen electrode over to the copper electrode, where copper ions are reduced to copper. So what's going on here is that the standard hydrogen electrode is being forced to run in oxidative mode. Hydrogen gas being oxidized to hydrogen ion and 2 electrons. The electrons going through the circuit and reducing copper ions to copper. So of course this would be the cathode where reduction is occurring, and the standard hydrogen electrode would be the anode where oxidation is occurring. Here we're showing what real solutions we might use. So in other words, instead of just writing here 1 molar hydrogen ion for the standard hydrogen electrode, we admit that we could use 1 molar hydrochloric acid. For the cathode, we're using 1 molar copper sulfate, which should look familiar. And if the beakers are attached by a fritted glass membrane, of course anions would flow toward the half cell that's losing electrons. In this case, it would be the standard hydrogen electrode. And cations would flow toward the half cell that electrons were coming into to maintain charge neutrality. The interesting thing here is that you'll notice that the voltmeter is reading plus 0.34 volts, and that's exactly the reading that we have here in the table for the copper 2+ being reduced to copper metal half reaction. Well, how about the system on the right here? Well, in this instance, we have a zinc 2+ zinc half cell connected to the standard hydrogen electrode. And when we do that and connect all of this up, we have, just to remind you, zinc sulfate in this beaker, 1 molar solution, 1 molar solution of hydrochloric acid in the standard hydrogen electrode half cell. And when we do this, electrons flow in the opposite direction to what they flowed for the copper example. In other words, zinc is being oxidized to zinc 2+. Oxidation is occurring here, so this is the anode. And electrons are leaving the zinc half cell and going over into the standard hydrogen electrode. And here, hydrogen ions are being reduced to hydrogen. So the standard hydrogen electrode is now running in reductive mode. Well, what do we have for a reading on the voltmeter? Well, the voltmeter now reads minus 0.76 volts. And lo and behold, that's the value listed for the zinc 2 plus zinc system on the table of standard reduction potentials. As I note here, this all looks like magic, but the magic ends if you don't keep the voltmeter hooked up in the same way. So in other words, I didn't switch the leads on the voltmeter. We've always got the standard hydrogen electrode connected to the black wire, the negative side of the voltmeter. In any event, you can see that defining the standard hydrogen electrode as 0 is a good way to assign or actually measure reduction potentials for these reductions that are listed in the table of standard reduction potentials. So we're using the standard hydrogen electrode as a reference. Let's look at another example. Suppose you took a strip of aluminum metal and you put it in a beaker containing a solution of 1 molar aluminum 3 plus ion, and you connected that to a standard hydrogen electrode in a manner similar to the copper and zinc half cells on the previous slide. Let's write out the expected redox reactions occurring in both the aluminum half cell and the standard hydrogen electrode half cell and calculate the expected overall potential. Well, if we look at the table of standard reduction potentials, we can find the reactions that are relevant here listed. We have, of course, the defined reaction of 2 hydrogen ions being reduced to hydrogen gas, defined as 0. That would be the standard hydrogen electrode. And the half reaction involving aluminum 3 plus and aluminum metal is listed here. The reduction is listed as having a reduction potential of minus 1.66 volts. Well, what's going to be oxidized and what's going to be reduced? Well, it appears from looking at these values in the table that the reduction of hydrogen ion to hydrogen gas is more favorable than the reduction of aluminum ion to aluminum metal. How do we know that? Because the reduction of hydrogen ion to hydrogen gas has a more positive E0 value. 0 is definitely more positive than minus 1.66. So what we decide is that in our setup, hydrogen ion is going to be reduced to hydrogen gas. In other words, the SHE will run in reductive mode, which means what's going to occur in the other beaker is that aluminum metal is going to be oxidized to aluminum ion. So the expected redox reactions would be hydrogen ion being reduced to hydrogen, aluminum metal being oxidized to aluminum 3 plus ion, each one losing 3 electrons. So our standard hydrogen electrode is the cathode. The anode would be the beaker with the aluminum metal and the aluminum ion. And the overall E cell would be 1.66 volts. This is getting the overall E cell by what could be called the old method. If we use our newer method of getting the overall E cell, we would take the value off the table for the standard hydrogen electrode and subtract the value right off the table for the aluminum 3 plus aluminum half cell, and we get an overall E cell of 1.66 volts. Now, for those of you who can't tolerate leaving reactions unbalanced, if you balance the reaction, it should look like this. My students and I have done a fair amount of electrochemistry in the research lab over the years, and we've never used a standard hydrogen electrode. A practicing electrochemist would find that pretty challenging. And as an aside, the standard hydrogen electrode is many times called a normal hydrogen electrode in the literature. There are other stable and reproducible reference electrodes that are easier to make and use in the lab. One common example that I've used and my students have used a lot in the research lab is called a saturated calomel electrode. Calomel is the common name for an ionic compound called mercury 1 chloride. Mercury 1 chloride has a very odd formula. In fact, this is an example that can typically drive general chemistry 1 students crazy when they're learning how to write formulas. Most likely because we normally tell students that ionic compounds should be written with the lowest common ratio of cations to anions. So 2 to 2 looks like we're breaking those rules. If you look a little more closely at this compound, you find that it's 1 ion of a 2+ charge with 2 chlorides. This mercury 1 ion is actually 2 mercury atoms as a group with an overall 2+ charge, so each mercury has a +1 charge, thus the formula. Well, in any event, what does this saturated calomel electrode look like? This is a sketch of one that we've used, and it's made by a company called Bioanalytical Systems. Remember, the redox reaction in any reference electrode should be able to be run in either reductive or oxidative mode. So let's look at the possible redox reactions in this reference electrode. One is the reduction of mercury 1 chloride to elemental mercury. And this, of course, would be a reaction running in reductive mode. The other would be the oxidation of elemental mercury to mercury 1 chloride. That would be the reaction running in oxidative mode. Well, how is this reaction attached to another half cell? We have here in this glass tube a saturated solution of potassium chloride. This acts as a salt bridge over to where we would dip this reference electrode, you could say in the beaker, running the other half reaction, and the interface would be a fritted glass disc. This would allow the flow of ions and not the direct mixing of solutions. We need to connect the reference electrode to the outside world through some sort of wire. So here we have a platinum wire that's embedded in the glass and sitting in this pool of liquid mercury. It comes outside, you wrap it around this little glass post because the wire is pretty fragile, and then you can connect your alligator clip right to that glass post. The saturated calomel electrode, the SCE, is actually 0.24 volts positive of the standard hydrogen reference electrode. Remember, even if we're using a different reference electrode in the lab, the standard hydrogen electrode, when we refer to it, is still defined as exactly 0. Hopefully this line graph will help. Here's a line. This is supposed to be voltage, positive voltage to the right, negative voltage to the left. And remember, the standard hydrogen electrode is rigorously defined as 0 on the scale. So when we say that the SCE is 0.24 volts, positive 0.24 volts relative to that, we mean it's plus 0.24 volts on the positive side of the standard hydrogen electrode. How would this play out in the research lab, or in other words, when we actually are connecting this reference electrode to another half cell? Well, remember on the previous slide, we had a half cell where there was an oxidation reaction of aluminum to aluminum 3+, and we found out that it has an overall potential of plus 1.66 volts. That was referenced against the standard hydrogen electrode. If we reference this half reaction, in other words, attached it to the saturated calomel electrode, we get a potential of 1.42 volts, a difference of 0.24 volts. So this half cell is 1.66 volts versus the SHE, but 1.42 volts versus the SCE. You can see this clearly, I think, by reproducing our line graph. We have the standard hydrogen electrode at 0, the saturated calomel electrode at plus 0.24 volts relative to that. We measured on the previous slide, or calculated, that the aluminum 3+ half cell is 1.66 volts versus the SHE, which means it would only be 1.42 volts referenced against the saturated calomel electrode. So when you report a potential, you normally would want to report it versus the reference electrode that you used. So if I were to report this value, I'd say 1.42 volts versus the SCE, or 1.66 volts versus the standard hydrogen electrode. This allows others to compare their work with yours.